This lecture deals with automata generating output, that is Moore machine. So let us consider an example. So assume that you are having two states Q0 and Q1. Let the output associated with each state be 0 and 1 respectively. So you are having A transition here, B transition, so this is a simple example for a Moore machine. So if we analyze this particular model, so it is clear that associated to each state there exists an output. If we consider Q0, 0 is the output associated with Q0. 1 is the output associated with Q1. So Moore machine is a finite automata generating output in which output is associated to each and every state. Associated to each and every state there exists an output symbol. And again, if we analyze this model, input symbols are actually A and B. So there exists unique transition for the input symbols A and B. In the sense, this is basically a deterministic model in which output is associated to each and every state. So what happens if I feed input A, B, B, A? So without consuming anything, machine will enter into start state Q0. So without consuming anything, it will enter into start state Q0, and whenever machine reaches a state, it will add the output symbol associated with that state to output string. So it will generate output. So without consuming anything, it will enter into Q0 generating output 0. Now from Q0, it will read input A. From Q0, by reading A, it will come back to the same state Q0, and the output associated with Q0 is 0. So it will generate output 0, and that output will be attached to the current output string. Now machine is in state Q0, it will read input B. From Q0, by reading B, it will go to Q1, and the output associated with Q1 is 1, and that output symbol will be attached to the output string. Now from Q1, the input is B. From Q1, by reading B, it will again reach back Q1, and it will generate output 1, which will be attached to the output string. Now from Q1, the input encountered is A. Machine will go to state Q0, generating output 0. So if we apply input string A, B, B, A, it will generate the output string 0, 0, 1, 1, 0. Now from this you can have, or you can identify one important property of this Moore machine. If input string is of length 4, it will generate output of length 5. 1, 2, 3, 4, 5. In general, if input string is of length n, Moore machine will generate output string of length n plus 1. The reason is that without consuming anything, it will enter into start state generating an output of length 1. So from there onwards, for further input strings, it will generate output symbols of length 1 that will be attached to the output string. So for input of length n, Moore machine will generate output of length n plus 1. Now let us formally define this Moore machine. So this Moore machine is formally defined as M equal to Q sigma delta delta, this is capital delta, delta delta lambda Q0. So you can define Moore machine using a 6-tuple representation, Q sigma delta delta lambda Q0, where Q is the non-empty finite set of states. Sigma is the non-empty finite set of alphabets or input symbols. Then capital delta. So delta is the non-empty finite set of output symbols. Then delta. Delta, as you all know, it's the transition function. Transition function that maps from Q cross sigma to Q. As I said earlier, this model is actually a deterministic model. So transition function will be same as that of DFA, deterministic finite automata. So transition will map from Q cross sigma to Q. Then next one is lambda. Lambda is the mapping function. Mapping function that maps from Q to delta. That is, lambda is the mapping function that maps state to output. Associated to each state there is an output symbol. And Q0 is the start state, or you can call it as initial state. So if we go through this formal definition, Q, sigma, delta and Q0 are exactly same as that of a deterministic finite automata, and this capital delta is an additional component which is the non-empty finite set of output symbols, and lambda is an additional function that actually maps or associates output symbol to state. Then again, if we consider this formal definition, you can say that set of final states is not there. So if we consider this transition diagram, there does not exist any final state. If we consider finite automata, that is DFA or NFA, there exists a final state. At least there will be at least one final state. In the sense, those models actually acts as string acceptor. Here, this model will not act as a string acceptor. It actually generates output string for a particular input string. So this is the formal definition of a Moore machine. Now, when we talk about the representation, different representations of Moore machine, first one is transition diagram. Transition diagram. So this is the equivalent, this is the transition diagram for a particular Moore machine. And the second representation is mathematical representation. So I can mathematically represent this Moore machine as m equal to q sigma delta delta lambda q0. So what is q here? Q is equal to, you are having two states q0 and q1. So what about sigma? You are having two input symbols a and b. What about delta? You are having two output symbols 0 and 1. So delta is set 0, 1. So if you consider output string is actually combination of zeros and ones. Then you can define transitions. Delta q0a, this is equal to delta q0a is equal to q0. Now delta q0b, from q0 for b it will go to q1. Next one is delta q1a, from q1 a transition goes to q0. Now Q1 B. From Q1 B transition will remain in the same state Q1. Now we can define the next one, that is lambda. Lambda, as I said, it's a mapping function that maps state to output. So lambda Q0, what is lambda Q0? Lambda Q0 is 0, that is the output associated with Q0. Now what is lambda Q1? That is the output associated with Q1, that is 1. So that is the reason for defining lambda as mapping function that maps from Q to delta. If you take function lambda, it receives an element that belongs to set of states Q as parameter, and it will give the result which is a member that belongs to delta. Okay. Now you can say that Q0 is the start state. So this is the mathematical representation of this particular model, Moore machine. And the third representation, so we have discussed transition diagram, mathematical representation, and next one is transition table. That is tabular representation of Moore machine. So you are having Q here. Here we can state output. So here you are having two input symbols, A and B. You are having state Q0 and Q1. You have to designate the start state using an incoming arrow. So what is Q0A? Q0A is Q0. Q0B is Q1. And if you consider Q0, the output associated is 0. Now what is Q1A? Q1A is Q0. What is Q1B? Q1B is Q1. And the output associated with Q1 is 1. So this is the tabular representation. Now how will you determine the output generated by a Moore machine for a particular input string? So if you consider the input string A, B, B, A, the output generated will be, so from Q0, so without consuming anything, it will enter into start state generating output associated with Q0. Now from Q0, for input A, it will remain the same state generating output associated with Q0. Now from Q0 by consuming B, it will go to Q1 generating output associated with Q1. Now from Q1 by consuming B, it will remain in the same state Q1 generating output associated with Q1. Now from Q1 by consuming A, it will move back to state Q0 generating output associated with Q0. This will be equal to, what is lambda Q0? Lambda Q0 is 0. Lambda Q0 is 0. Lambda Q1 is 1. Lambda Q1 is 1. And lambda Q0 is 0. That's it.